In today's video, we'll take a look at AdaMax Optimizer, an improvement on Adam who doesn't require bias correction for the scaling factor. So the scaling factor of Adam look as follow, and if you watch my previous video on Adam, you understand that this is a running mean, and this is the second running mean in the formula. So this formula over here will scale the gradient inversely proportional to the L2 norm of the past gradient and the current gradient, meaning as this scale factor goes up, the gradient magnitude will go down. So AdaMax modify the L2 norm to be an L infinite norm, which when derived converge to the following formula below. If you want to look at the derivation, you can check the paper that I've put in the reference in the description. So the max function that is defining ut, which is similar to vt, is why this method is called AdaMax. So the whole thing gives us the following formula and the component that we have. So we're going to go through each one of them one by one and understand every parameter. Afterward, we're going to dive into a Python implementation so that we really understand how this is working. You will see in the Python implementation, it's really similar to Adam. So here theta at t plus 1 is the updated parameter values. The theta at t is the current parameter values, and those are usually vectors. N is the learning rate, usually set at 0.002. This is what the paper AdaMax recommend. UT and MT are the main component of AdaMax. We're going to go into UT and define what it is. So like you checked before, this is the L infinite norm and of the gradient, and what we see is after the derivation we have max of beta 2 times the previous VT or the previous UT and the gradient, the absolute value of the gradient at time t. So B2 over here, beta 2 is it's a hard set parameter at 0.9999, and it's considered the running mean, but since we've gone through the derivation, it looked like this. It's not a running mean anymore, but it's similar to the formula above. Vt minus 1 is the previous scaling factor value, so we keep track of them, and the gradient is obtained by doing a partial derivative of the parameter. So next up we have m hat at t, which is equal to a bias corrected mt value. So this is similar to Adam, so this is exactly the same thing actually. So the component below, the divisor, we have 1 minus b beta 1 at t. So beta is actually the decay factor, the first one. So this is equal to the decay factor exponent the current timestamp. So this is to avoid the bias towards 0 in the early step. So finally we have mt, which is equal to this. So this is a standard running mean of the gradient with b1 equal to 0.9. And that's pretty much it. Let's now jump to a Python implementation to check out how to implement this whole thing. Alright, so here we are in the notebook. It's the same notebook for all of the optimizer that I've done before. So if you want to take a look at them, you can click over here. And now we're doing AdaMax, and the basic idea is that we're trying to apply AdaMax to a line, which it was not made for this, but it still works as a proof of concept. So here you can see like how we implemented the line. It doesn't really matter. This is how we're going to derivate the whole parameter space to get the partial derivative. And the only thing that really matters is here how we stochastically sample one element, but this is just like sampling with replacement. And the only thing that matters is actually AdaMax over here, right? So I would suggest looking at AdaMax, but also look at Adam, because it's almost the same thing. If you look at the structure here and the structure here, it's literally the same thing except one region. So we're gonna go through the thing. We first have the input, right? So those are the input. We have the model we have our x and our y's that are the data points. We have those parameters which are set given the paper. So this is learning rate, the beta 1, beta 2 running average, decay factor, and then the maximum number iteration, because we're gonna kind of overfit on the data set. So this is the input. The output is just the model being fixed. And what we're trying to do is we're trying to do the intercept 0, slope of 1 line. So with those data points, we're also trying to do intercept 0 and slope of 2. And finally, we're trying to do intercept of 1 and slope of 2. So those are those points represent those. Perfect. So we can dive into the formula. We have some variable initialization over here. If you looked previous video, I was actually trying to hard code 2, but here this function can actually accept any number of parameter. So this is it's actually any number of, there you go. Okay, so we have m, which is the one of the variable. We have m at t. This is the m which is unbiased. We have the v in the formula that I presented. It's written u, just to not confuse it with Adam, but it's the same thing. It's v. This is the L infinite norm, and which actually is a scaling factor for the gradient. This is the gradient that we keep tracked as we go. So that's the initialization, and this is where we're gonna iteratively fix our stuff. So this is stochastic. So if it's stochastic based, you're gonna take some amount of samples stochastically, and you're gonna run the thing on a batch over here. Here we have a batch of 1. So we stochastically sample from the x's and y's, like the two of them together, and we get an x and a y. And then over here, we're gonna get the partial derivative with this function. So we have all of our gradient that we need. So how much we should change this in which direction, and then we're gonna update the m and the v parameter. There's a lot of stuff because it's a line less comprehension, but what's really matter is this. The m stay the same as Adam. If you look over here, it's literally the same. So if you watch my previous video, you can understand this. This is just a running average that we're doing with the past m and the gradient that we're looking at, and we're iterating on both of them at the same time. This is where we have the max of beta 2 times vi, the previous v for this parameter, or the absolute value of gi, right? And remember, those are vector, so we're actually going to do it on each of the element. This is where we're going to bias correct for m, right? So it's m divided by 1 minus the beta at t at 1 exponent t, and if you look at Adam, it's the same thing for it, except the only difference is the v. We're not going to bias correct it because it's the infinite norm, and we're fine with that. Okay, so here is where we update the parameter. It's a long one because we're iterating on 3 things at the same time. So weight, the v's, and the m that are corrected, and we're doing like parameter by parameter. And this is the new weight is equal to the previous weight minus learning rate divided by v times the m that is corrected. And we have those I because we're doing weight by weight. And that's pretty much that. If we run it, get pretty good result fast. So after 100 reiteration, we're already like pretty much done, and then you just converge better. Here it's supposed to be 0 and 2. Yes, not too bad. It's not too bad. And then this is supposed to be 1 and 2. 1 and 2. Good. This is good enough. So that's pretty much it for AdaMax. If you look at Adam, it's pretty similar. The only quirk is that the V is different. Alright, that's it for today's video. I hope that you enjoy it. If you have comment or question, you can leave them in the comment section. And like always, have a great week.